Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel Chemistry, the Mystery of Molecules. Today's topic of discussion is phase transfer catalyst or PTC. It's a widely used, very important chemical reagent. So we shall learn today about its preparation, reactivity and application in organic synthesis. So this is the most important thing. Before going to details, one MCQ. So you can see the MCQ, which metal ion binds most selectively with krypton 222 ligand in solution. 4 options are provided. I request you, please pause the video, try by yourself and write your answer in the comment box, and don't hesitate because self-evaluation is essential for improvement. Now let's go to the main topic. And by the way, before going to details, I am sorry because my voice is not good today. Now, so what is actually a phase transfer catalyst? This phase transfer catalyst is a kind of a catalyst that facilitates the migration of one reactant from one phase into another phase where the reaction occurs. So every word is important. I shall explain throughout the discussion. Just listen right now and remember one important information. This phase transfer catalyst is a kind of heterogeneous catalysis. In your viva, examiner can ask, what do you think phase transfer catalyst actually is? Is it a homogeneous catalyst or is it a heterogeneous catalyst? Because homogeneous means soluble, PTC is soluble, but question why this is heterogeneous? Because in this case two reaction layers where reactants are there, they are immiscible together, so that's why it is heterogeneous catalyst. So it is interesting, and by the way I have already discussed about heterogeneous catalyst on dedicated lecture, so you may visit for better understanding. Now, so the question comes here, when we need a PTC, question number 1. So we need to bring all the reactant in the same phase or in solution where the reaction is happening such that they can react together efficiently. When both or more reagents are in different phase, PTC plays the important role. As I told some time before, it brings from one phase to another phase where the reaction is occurring. So that is the role of PTC, means bringing all the reactant in a same phase. Now question, can we call it as a catalyst? Obviously yes, we can say it's a catalyst because it participates in the reaction but at the end it remain unaffected. I shall give some example after some time. So from that you can say that okay, this is a catalyst, and more specifically if I say it is a heterogeneous catalyst. Now look at this example. So first what we have taken in this case, for example, this is an organic solvent, any organic solvent. For example, you can consider this is ethyl acetate, ETOAC. Now if you take this C8, 8 carbon chain alkyl bromide, so it will remain inorganic solvent, so it is an ethyl acetate solvent. So the reactant 1 is inorganic solvent. Now second reactant is sodium cyanide, and by the way sodium cyanide is in salt, so it will not remain in this organic solvent. So you can say these small granules are NaCN, sodium cyanide. Now since they are not in the same phase, so reaction can't happen. In this case what is done, for example, you add some water here. Okay, so this layer is the aqueous layer. Now what will happen, this if you shake little bit, this sodium cyanide from here it will go this phase and it will remain is aqueous phase, so aqueous sodium cyanide. Now question, will the reaction happen? By the way, reaction will happen but in a very slow rate. Why? Where the reaction will happen and how the reaction will happen? Reaction will happen because you see there is this is called interface, means the contact between this aqueous versus ethyl acetate layer, and by the way water and ethyl acetate are not miscible to each other. So in this interface reaction can happen but reaction rate will be very slow. So consequently how this thing could be done? By addition of a phase transfer catalyst, for example R4N plus, you may consider it's a Cl minus. Okay, so what we have understood that it's an immiscible reagent, means this, so immiscible, actually these two are reagent, this NaCN and sodium, this alkyl bromide and sodium cyanide immiscible together, two different kind of solvents and not miscible and different phase. This is aqueous phase, this is organic phase, and in this case heterogeneous catalyst or phase transfer catalyst, in this case R4NC. So what happens in this case? See, it's an aqueous solution, sodium cyanide, so it will ionize. You can consider two, sodium plus ion and cyanide minus ion, and by the way negative charge is concentrated over the carbon atom. Now Cn minus. So exchange will happen, means this chloride could be exchanged with this cyanide, and ultimately what it will produce? It will produce R4N plus Cl minus. Now question is, what is the solubility of this R tetra alkyl ammonium chloride? It is soluble in both organic as well as aqueous. Why? Because it is an cationic anionic species, means quaternary ammonium salt. So for that purpose it is soluble in aqueous medium, since it is a salt. And by the way, there are 4 alkyl group bulky chain, that's why it is soluble in ether. Now if you add small amount of this quaternary ammonium halide, it will be present in both medium. So it will be present in both medium. So what will happen, that in both phase there will be NaC, this Cn minus, better to say, as quaternary ammonium cyanide. So I guess you have understood, and since they come into the same phase, then reaction will occur. Now simple thing, without a PTC, how reaction expected to occur in the heterogeneous system, organic and aqueous? As I told, it will happen in the interface. So now we shall explain the mechanism after some time in little details. Now in this context, another explanation is that law of mass action based explanation. What is that? That is, in chemistry, the law of mass action is a proposition that the rate of a chemical reaction is directly proportional to the product of the activities or concentration of the reactant. Now in a particular phase, you can consider the concentration of two reactant, means this both A and B is with, this is actually, this Kf is rate constant, so this is the concentration multiplication and this is the rate of reaction. Now just consider, if concentration of either A or B increases, then reaction is expected to happen faster. Now go to the previous example. In this case, this alkyl bromide, for example, let's consider this is A. It is completely soluble in organic phase, so it doesn't matter, but the concentration of this cyanide anion, which is the nucleophile here, matters. So in this case, what will happen? Initially it was not soluble, so no reaction. Now 0. Now no reaction. Now after, in the interface, very small rate, means low rate reaction, but whenever you add cyanide minus quaternary ammonium salt, then the cyanide will come into the organic medium. Consequently, the concentration of cyanide in the organic medium will increase, and through SN2 type reaction they react, and rate of reaction is proportional to the concentration of A, we understood, and the concentration or activities, you may consider the active mass of this cyanide anion in the form of quaternary ammonium cyanide will dictate how the reaction will happen. Since it is more in concentration, rate is more, so reaction will happen more efficiently, and the ultimately alkyl cyanide will be obtained. Okay, so now we have understood. So is there any alternate choice of PTC? Because we should not depend on a particular chemical. Yes, possible. If you use dimethyl sulfoxide or N-dimethyl formamide, they are highly polar and they are capable to solvate both organic and some inorganic salt also, like this sodium cyanide. But they are actually, student, very costly reagent. First point number 1. Second, they are very high boiling, so by distillation you can't remove them. And third is how they are purified. They are purified with aqueous workup, for example water acetate, ethyl acetate type workup. So in this case also large amount of solvent needed, and purification is really difficult. And not only that, this NMP, N-methyl pyridone, they have even further boiling point. So these are alternate, but these are costly and difficult to handle. So that's why it is better to use PTC, and that's why you see industry uses this phase transfer catalyst in a huge, means bulk scale, and the total benefits we shall learn after some time in a summarized way. So we have understood about this, that PTC is very important. Now let's know that how many types of PTC possible. There are many types of PTC possible. For example, this is quaternary ammonium salt, this is phosphonium salt, this is crown ether, and this is krypton. Now the most important thing, if you look at this, potassium solvation is maximum in this krypton 222, and by the way, I guess you got the answer of your MCQ. So now question is, since I told that it is industrially used widely, now always industry thinks few points, for example cost, environmental impact, etc. So this ammonium is the best choice for that. That's why you see in industrial processes quaternary ammonium salts are used. So now our focus will be on quaternary ammonium salt. So in this case, this ammonium salt is the cheapest one. Now let's learn how this quaternary ammonium salt are prepared. This is Menshutkin reaction. How? In this case, this tertiary amine reacts with alkyl halide, and by the way, this is student alkyl halide, not aryl. Why? Because if I say aryl, then there should be this arene or this benzene halogen bond. This is aryl halide, but this is alkyl. This is benzyl halide because this is CH2. So please don't get confused. Now, so what happens in this case? This lone pair attacks here and ultimately it leaves, and via a SN2 type reaction it produces this quaternary ammonium chloride, or you can say this triethyl benzyl ammonium chloride. And by the way, sometimes we say that triethylamine is a specific proton scavenger, means it abstracts proton significantly, but it can act as a nucleophile also. For example, I have already discussed a dedicated lecture about acyl nucleophilic substitution reaction where triethylamine is used as a base, but in the first step it acts as a nucleophile and the intermediate is isolated. Proof of the mechanism I have given. So you may visit that video for interesting knowledges. Now, from this thing we have understood that this is actually a kind of PTC where one benzene nucleus is there and other parts are alkyl group. Now, a question may come in your mind that, sir, why don't we try to prepare this PTC directly from alkyl halide and ammonia? Because we have previously read that alkyl halide and ammonia, if we react, it ultimately ends up quaternary ammonium halide, means exhaustive alkylation possible. Yes, student, that's true, happens. How? Similarly, like SN2 reaction, first it attacks, it leaves. So in this way it produces this RNH3X. So in this way reaction goes on step by step, and ultimately this is produced quaternary ammonium X plus 3HX. Why 3HX? 3 hydrogen from this ammonia and 3 from here, and fourth one is there as a counter anion. So this thing we have understood, and why don't we prepare PTC by one step? It is easier, less time consuming, and since we are talking about industry prefers such kind of thing and it is expected to be cheaper. But there is an issue. Issue is that, first of all, if you look at this R, what is the general nature? Generally R is a long alkyl chain. For example, you can take a 8 carbon. Sorry, this is 1, 2, 3, 4, 5, 6, 7, 8. So this is a 8 carbon alkyl bromide. So if you do the reaction with ammonia, you can't expect that quaternary ammonium halide will be produced in that step because of the bulkiness, means this R4 groups are very bulky. So directly in one step you can't prepare. That's why what people do, they take a amine. For example, just some time before, as I told, a triethyl amine. And along with that, in this case there are 2 carbon short fine. They use a very bulky, for example C12Br, C12H2425, C12H25Br. Now in this case what you can expect, that this H25Br, it's a very big group, so reaction will happen and ultimately it will produce another type of quaternary ammonium halide, and that is soluble in both organic as well as aqueous. So that is the best thing. And in this case what I can say, so point wise, first bulky substance cannot be produced. If this is small, for example tetramethyl ammonium halide, if you want to prepare that thing, that possible, you can say fine, but for long chain like this it is not possible. Point number 1. And point number 2, we can't get unsymmetrical PTC or PTC having very long carbon chain. Means just sometime before, you see here this PTC is a unsymmetrical PTC. Now whatever reaction you are trying to do, you have to choose reagent accordingly. So you need to tune the substitution such that you can achieve a particular chemical reactivity, and for that purpose this one step is not a good method. Two step means the previous one is better. Now, so what is the benefit of this PTC in overall? In this case reactivity is higher because 2 solvents are immiscible. Reaction may happen on the interface, but right now after addition of PTC in organic phase, concentration of both reagent increases. So lesser temperature and time needed because concentration means of the 2 reagent in the same medium increases. Second thing, if you look at the reaction, for example how this is happening, now you say this is actually an X plus these are 4 N plus and this is a Cn minus, and in this way what it produces? It produces this Cn. Now I guess you have understood the overall reaction is an SN2 type reaction. Now SN2 type reaction means nucleophilicity of this ligand is the important thing, okay, and since in organic phase what is there? Tetraalkyl ammonium cyanide, it is the thing. Now this R4 means this nitrogen is attached to 4 bulky groups, so hydrophobicity there, and second nitrogen is charged. So in order to maintain the electroneutrality, although this cyanide is closer to this quaternary ammonium salt, but it is not directly bounded, or there means it is not directly bounded, so it is, you may consider, bare, naked or free. And when the nucleophile is free or less solvated, then the reactivity of the nucleophile enhances significantly. That's why in presence of lesser temperature or shorter time, you can get the complete conversion, and in this way the obtained byproduct amount is also less, so it is relatively more pure. So that's why you can conclude that this is a relatively green process and industry likes it. That is the main thing why PTC used extensively. Second, solvent choice increases. For example, DMS or DMF, such kind of high polar, high boiling sorbate could be replaced by relatively cheaper solvent like ethyl acetate, acetone or water. And by the way, in this case, if you check this ethyl acetate and water, they are not miscible. And by the way, student, please don't get confused. Remember one statement: acetone and water highly miscible together. So this concept is applicable for ethyl acetate and water mixture. And since means in this case, this water, since we are using, means you can consider this is the most benign reagent, so that is another advantage of this process. Now in this case, inorganic and ionic reagent could efficiently be used in organic reaction. Now in this context, the use of water comes because inorganic or ionic reagent or salt, those kind of chemical is not soluble in organic medium, they are soluble in aqueous medium. So that's why you have to take one water medium. Another thing, organic solvent doesn't get soluble in water, so you need to take another organic solvent. So that's how you can balance the reactivity using this phase transfer catalyst. Now in this case, please remember the workup process is relatively easier because the two layers are separated and reaction is happening in the organic medium and product is in the organic medium. Since these two layers are separated, so using a separating funnel, like this, you can separate the this product very easily. So that's why purification is also easier. How? By collecting first collect the organic solvent and then evaporate the organic solvent and do a column chromatography easily, such that, because in organic solvent two reagent you can get, first of all the product and second small amount of this PTC or phase transfer catalyst. So using a small column chromatography you can get the target product. So that's the overall thing. Now let's learn about its application. If you look at this reaction, this is an SN2 reaction of octyl chloride and sodium cyanide. You can see in their reaction doesn't produce anything, so no reaction because not miscible. Now in this reaction medium, if this tetrabutyl ammonium bromide is added, then it is produces. But by the way, there is no mention of water here, how the reaction is happening. So sodium cyanide is insoluble, means it's a different phase, but in that case also it can react with this quaternary phosphonium bromide, which is in the organic phase. So anion exchange can happen, and in this way it will produce this NBu4P plus cyanide minus. So now in this way cyanide will come into the organic medium and reaction will end up into this alkyl cyanide product. Similarly, cyclopropane preparation, if you look at, this is a chloroform alkene in presence of sodium hydroxide produces this cyclopropane derivative, but this reaction happens in aqueous medium. Now this chloroform is in organic medium, it's organic solvent and it doesn't mix with water, so reaction doesn't happen because this chloroform and sodium hydroxide need to come closer, and in this way it will produce this dichlorocarbon, and this dichlorocarbon actually reacts with this double bond. Okay, I have already discussed Reimer-Tiemann reaction where you can see similar kind of reaction mechanism, and this dichlorocarbon is actually a singlet, means this is a vacant p orbital and this is the lone pair. So first you can see this double bond will attack, second this lone pair will attack. So I have explained this thing dedicatedly in a dedicated videos, so you may visit. So it will produce, this is a cyclopropane derivative. But without a PTC, the reaction doesn't happen, as this carbene could not be generated into the aqueous medium. And for that purpose, what is taken? One organic phase, means this chloroform phase, this PTC and the other reagents. And in this case, the used PTC is this one, this benzyl triethyl ammonium halide. So in presence of PTC means this hydroxide means this OH base goes to the organic medium, and in organic medium it reacts with chloroform, deprotonates it, and ultimately through leaving of one halogen it produces this dichlorocarbene. So we can understand what is the mechanism of this process, and that's why this is very much important. So different phase is happening very smoothly, and in this case this is aqueous phase and this chloroform phase, organic phase, where this chloroform and alkene there. Now another example is purple benzene. By the way, student, benzene is colorless. Purple benzene means because of presence of this permanganate anion. I shall not say potassium permanganate, it's a permanganate anion, because permanganate is coloring, and this is a strong oxidizing agent. So what happens? If you want to do any reaction, a particular reaction or oxidation reaction using permanganate as an oxidizing agent, in benzene reaction will not happen, because permanganate is a salt, so it will not soluble in benzene, which is an aromatic hydrocarbon. But if you want to do this reaction, you can do how? You can take a crown ether. You may consider this is a 18 crown 6 type. It's not exact because this cyclohexyl group, so it's that type of thing which selectively solvates K plus, and in that's why potassium goes into the benzene medium, because this moiety, this organic moiety is soluble in benzene, and this potassium is encapsulated in such way, means it is extremely stabilized, so it also goes. Means first of all, the ADAC formation between this crown ether and K plus is very favorable, so ADAC formation will happen instantly. And since this organic moiety is soluble in benzene, so this potassium crown ether will go. Subsequently, along with that, this permanganate will go into the organic medium in order to maintain the electroneutrality, because positive charge is going into the organic phase. Obviously negative charge will go. Charge don't like to remain separated in separate medium, so that's the uniqueness. So in benzene medium you can get the property of permanganate, means an oxidizing agent, because of this 18 crown 6 means crown ether complex. So that is the uniqueness of this purple benzene. Now, in conclusion, what you have learned today, that this PTC is a green chemical and it is soluble in both aqueous and organic reaction medium because of two. Aqueous means this N plus charge, and organic means the substituents, means 4R, means R4N. So this, it requires relatively less drastic condition, means temperature and time, so it is less energy demanding, and that's why it is good for green chemistry point of view. And finally, it allows the use of water, which is the greenest solvent, student, in organic transformation, and it allows the direct use of salt, as I told some time before, sodium cyanide for the organic reaction. So this is the overall learning for today. Now let's come to the MCQ. As I told, which metal ion bind most selectively to krypton 222 ligands in the solution? I have given the answer in between the discussion. So again I am telling, the answer is option C, potassium. So this is the end of the discussion. Thanks for watching. If you really enjoy my teaching, then please help my channel to grow, and I request please visit my another channel, that is Climate and Chemistry, where I upload global warming and climate change related videos. So thank you again. Stay happy, stay blessed. See you in my next video. Bye bye.